Calculating the centripetal force and the centripetal acceleration for an object moving with uniform circular motion. By uniform we mean steady, smooth, constant speed in a circle. The centripetal force, F sub c, is equal to mv squared over r. As you see over to the right here, F sub c is centripetal force. Centripetal force over here on the right will be measured in newtons, will come out in newtons. The m stands for the mass in kilograms. V is the velocity, the linear tangential velocity in meters per second. It will be really the speed, which will be constant here. And then the radius of the circle of motion. A sub c is v squared over r. For some reason the formatting of my subscripts are not working out here on this video, but on the worksheet it's a sub c. The centripetal acceleration is the v squared over r, and as you'll see here, the relationship between F sub c and a sub c is that F, well, from Newton's second law, F net equals ma. In other words, if you multiply the acceleration times the mass, you get the force, and that's the connection between these two equations. F net, or F, equals ma. Here are a couple examples. Let's say you have a mass on a string, like a ball on a string, and you're twirling it in a circle of radius 45 centimeters. And the tangential velocity of the ball is 2.5 meters per second. Let's calculate the centripetal acceleration, part A here. So the centripetal acceleration, A sub c, will be v squared over r. Check our units. We want v in meters per second, which it is, so that's 2.5 squared. We want the radius in meters. It's given in centimeters. That converts to 0.45 meters by moving the decimal 2 places. So the centripetal acceleration comes out to be 14 meters per second squared. That acceleration is directed towards the center, even though the velocity, the tangential velocity, is, as we say, tangential to the circle as shown in the diagram. Part B, the centripetal force, F sub c, mv squared over r. You could take a shortcut and just multiply our previous answer times the mass, but I'll plug everything in here. Watch out for the mass. We want this in kilograms. That's 0.035 kilograms. 35 grams. It's 0.035 kilograms times the 2.5 meters per second velocity squared over the radius, once again, 0.45 meters. The centripetal force in this case comes out to be 0.49 newtons. And that would be directed towards the center. That's how tight the string is. That's the tension in the string pulling on the ball, keeping it in the circular motion. Here we have a car. Here's an overhead view of a car rounding a curve, so bird's eye view. Loosely speaking, I have a free body diagram. It's not really a free body force diagram. I just want to show you the perspective of all the vector quantities going on here. The velocity of the car is tangential to the curve as it rounds the curve here, but the force and the acceleration, which are always in the same direction, the net force, the centripetal acceleration, are towards the center of the curve of the road. Now we need to calculate the centripetal acceleration. Part A. Once again, it's pretty straightforward here. A sub c is v squared over r. Just check your units. A sub c, the velocity is in the proper units, 35 meters per second squared. Don't forget to square that. Over the radius, we're good here. If they give you the diameter, watch out, because as we know, the radius is half the diameter, but we do have the radius here, 55, but they could give you the diameter and just divide by 2 to get the radius. And if you work this all out, that comes out to be 22 meters per second squared as the centripetal acceleration. And then part B, what's the direction? Towards the center. So that's towards the center of the curve. I have that shown in the diagram. That's the answer to part B. Part C, what is the centripetal force? And once again, centripetal force is kind of a generic term for actual real forces. The real force here is friction that keeps the car on the road. If there's no friction, the car slides off the road into a ditch or into a tree, which you don't want to have happen. So friction is the centripetal force here. In the previous problem, the string was the centripetal force. For planets going around the sun or moons, the centripetal force is gravity. That's the specific force. Anyway, centripetal force is mv squared over r. And every unit here is good to go. 1,200 kilograms times 35 squared over 55. And we could have just taken our previous answer for the centripetal acceleration and multiplied by the 1,200. But if you do that, you get a pretty large force here. 26,700 newtons of friction keeping this car on the road. If you increase your velocity too much, friction cannot hold the car on the road. As you may have experienced or will experience in the future, hopefully not, you do not want to slide off the road by going too fast around a curve. And the direction is once again toward the center. So there we have it, calculating the centripetal acceleration and centripetal force, which are always acting toward the center of the curve of motion.